Hello viewers, today I'll begin an interesting topic called chemical kinetics. It is important for us in the laboratory as well as for those chemists who are working in industries. The lecture plan goes like this. I'll introduce you to the subject of chemical kinetics. Then we talk about rate of reaction, then factors affecting reaction rates, very important, by which we have to manipulate rate of reaction. Then we try to establish a relation between the rate and concentration of the reactants. And towards the end, I'll summarize what we have discussed in today's lecture. Chemical reactions. We come across hundreds of chemical reactions in nature, producing both organic and inorganic compounds. Let us look at some examples. Formation and destruction of ozone. We talk about ozone hole, you remember? Ozone is formed, and rate at it is formed, and the rate of destruction of ozone was in balance. But due to pollution, the destruction rate has gone up and there is a ozone hole. Photosynthesis, all of us know about it and its importance. This is a chemical reaction that takes place in presence of light. That's why the prefix photo is there. Formation of methane from biomass and biochemical reactions within our body, hundreds of them. Some inorganic compounds are thrown out when there is eruption of a volcano, but industries produce hundreds of chemicals. Chemicals that serve as drugs, fragrances, preservatives, surface coatings, and so many other applications. The process should be economically viable for a chemical reaction to be successful. And one factor that influences the economics is the rate of a chemical reaction. What is a chemical reaction after all? Chemical reaction is nothing but, simply put, making and breaking of bonds. Smaller molecules join together to give a bigger molecule, or a bigger molecule, we break it to smaller molecules. When we talk about a chemical reaction, three fundamental questions come to our mind. Consider a hypothetical reaction. A moles of A plus B moles of B gives you C moles of C and D moles of D. What we have written? We have written a stoichiometric equation. We have worked out. We are interested in, say, product D. We write the equation, try to balance it, and now we know if we carry out this reaction and if it goes to completion, we are going to get D moles of D. But questions still remain. The question that first we have to answer, is this reaction possible? A very fundamental question. How to answer this question? We have to go to thermodynamics. We have to work out the thermodynamics of this reaction. What do we do there? We try to find out the free energy change. If it works out to be negative for the reaction is feasible and it is going to be spontaneous. But it needs some elaboration. Simply because thermodynamics says that a given reaction is spontaneous doesn't mean that it's easy to carry out the reaction. Take, for example, the reaction between hydrogen and oxygen. We put them together in a flask and wait for the reaction to take place. The thermodynamics works out that the reaction is feasible. Even if we wait for 100 years, you will not see even a molecule of water formed. But then if you put a spark there, there will be an explosive reaction. Which means even when thermodynamics says that reaction is feasible, we have to find out the conditions under which the reaction takes place. So some spontaneous reactions are fast, some spontaneous reactions are slow. It is for us to find out the conditions under which the given reaction takes place. Then you can imagine if the thermodynamics says no, there is no point in trying a reaction, not at all. The second question that comes to our mind is how far this reaction will proceed. We are interested in knowing what's going to be our yield, and we try to get the answer from chemical equilibrium. Equilibrium constant for the reaction has to be worked out, and then we try to manipulate the conditions whereby we are able to push the reaction towards the right to get the maximum equilibrium yield. So it's for us to work out that. Again, here thermodynamics helps us because delta G is equal to minus RT ln K is the relation that we have. K is the equilibrium constant. The third question, how fast will it reach the equilibrium? A very good question at that, and thermodynamics is silent about it. Thermodynamics is bothered about the initial state and the final state. How the path is covered, thermodynamics is not interested. Where do we look for the answer? We look for the answer in the branch called chemical kinetics. Yes, this is the theme of the lectures that I am going to give. It is the branch that tells us how reactions take place and the rate at which reaction takes place. Chemical kinetics, sometimes called reaction kinetics, is a branch of physical chemistry that deals with the study of rates of chemical reactions, factors affecting rates of reaction, mechanism of reaction, and also it deals with theory of reaction rates. But as a common man, we have an intuition regarding the rates of reaction. Like if I take a pair of jeans, I know that is going to fade. I am waiting for it because faded jeans are the fashion. Similarly, a worker or a supervisor who has freshly cast a concrete slab knows how much time it takes for the concrete to set. He will pour water there and wait for a particular period of time because he knows by experience that this much time is required for the concrete to set. While some reactions are fast, some are slow. We know that one of the examples that we come across in daily life is the rusting of iron, a very slow reaction. If I buy a knife and leave it on the table, if I look at it every day, I will not see any difference. But if I come after 6 months, I will find that the rusting has started, and after a year, there will be more rust. So rusting of iron is a very slow reaction, whereas the reaction between sodium metal and water is a rapid, a fast, an explosive reaction. If I take a piece of metal, metallic sodium, and put it in water, and you might have tried this in the lab, at least those boys who are interested in playing mischief definitely might have tried this. But you don't try it, it's going to be dangerous. But it's a reaction which is explosive, instantaneous reaction. Now, every reaction requires some time for completion, at least it approaches 99.9% of the reaction. Between these two extremes, the fast and slow reactions, there are hundreds of reactions, both organic and inorganic, taking place with measurable rate at temperatures that can be easily attained in the lab. And such reactions are called normal reactions. They do not require sophisticated equipments to study. We can follow their rates in a normal physical chemistry laboratory. But we have a word of caution here. Those fast and slow have lost some meaning. What was fast yesterday, today we do not consider to be fast, because we have developed methods to study reactions that are over in a microsecond, a nanosecond, a picosecond. Now we are talking about femtosecond reactions. So that is beyond the scope of this lecture. We are bothered about normal reactions. So let us start with what is meant by rate of a chemical reaction. Rate of reaction means how much of a particular chemical is either consumed or formed in a stated interval of time. If I carry out a reaction for 10 minutes, what is the difference in concentration, say, of the reactant? That I would like to find out, and that gives us an idea about the rate of reaction. This is very important because the industries want to get the product quickly, because economic production of organic or inorganic compounds is of their interest. The success of a chemical process depends on the yield and how quickly that yield has been produced. Every day the production target is 100 tons, we should meet, and for that the rate of reaction should be optimum. Let us look at some of the factors that affect the rate of reaction. One is the nature of reactants. If I have a solid reactant, surface area comes to my mind, because if I use granular reactant and compare the rate at which that reacts with a powdered form of the same reactant, I see the difference. Surface area matters a lot. Surface area gives us higher area of contact between the reactants. Ionic reactants. You have carried out titration of, say, HCl against sodium hydroxide. You take sodium hydroxide in the burette and add dropwise, and at times you tend to add faster, where phenolphthalein is added as the indicator. You swirl it and you don't wait for several minutes or seconds also for the color to appear. Color appears when the endpoint is reached. The last drop you add and the color is there. A very fast reaction, because ions are very reactive. So the nature of reactant decides how the reaction is going to be fast or slow. One example I can give you here. You have also carried out a titration between potassium permanganate and oxalic acid. It's slightly slower. You are told to warm up the solution. You are told to add potassium permanganate initially dropwise. The reason being, this is going to be a very slow reaction initially. The rate picks up at a later stage. Concentration of the reactants. With the increase in concentration, rate of reaction increases, or if the concentration decreases, the rate of reaction decreases. So here we can look at, if you start the reaction, the concentration of the reactant goes down because the reactant is consumed. And naturally, when the number of molecules available for reaction are less, the rate is going to be less. That means you can draw a parallel between decrease in the concentration of the reactant and decrease in the rate of reaction. Both seem to be following similar trend. How exactly the two are related, we are going to see a bit later. Temperature is an important factor. We know how much time it takes us to, say, prepare a cake in a microwave oven because of experience. Our rate of reaction increases with increase in temperature. And the last of the factors is the catalyst. Use of a catalyst is an important thing that we do in industries, especially industrial processes, because we want to increase the rate of a chemical reaction. By adding a catalyst, it is possible for us to increase the rate of a reaction, and most of the industrial processes use this method. A catalysis therefore forms the backbone of chemical industries. How to determine rate of a reaction? Consider this, a simple reaction, reactant R gives us product, and we know that the temperature has to be kept constant when we study the rate of reaction. What do? We determine the concentration of R, the reactant, or that of the product during the course of the reaction at stated intervals of time, after 10 minutes, 20 minutes, 30 minutes, etc., depending on how fast or slow is the reaction. And we get a plot like this. The concentration of the reactant after stated interval, you can see, you can plot it, and you get a curve. The reactant concentration goes on decreasing. Similarly, if you monitor the concentration of the product, you will see that with the successive readings, you will get a concentration profile which finally levels off. And if you want to find out the rate, find out the concentration of the reactant or the product at time t1, and after sufficient long period, find say t2, you find out the concentration of the two, and then work out the time difference t2 minus t1, and what is the change in concentration that has occurred during this time period. We get say R2 minus R1 if we choose reactant to monitor the progress of the reaction, or if we look at the product concentration, it becomes P2 minus P1, and you can see the rate of reaction can be written as R is equal to minus dr delta R by delta T is equal to delta P by delta T. Delta stands for the difference in concentration, delta stands here for difference in temperature. We have used the negative sign because the reactant concentration decreases with time, and we want to express rate of reaction as a positive quantity. And also we must remember the rate that we get is the average rate. The rate of reaction changes with time, and therefore whatever rate that we have calculated is the average during that time period. Now look at some of the reactions, and you are familiar with this reaction. Inversion of sucrose. 1 mole of sucrose reacts with 1 mole of water to produce an equimolar mixture of glucose and fructose, 1 mole, 1 mole. What do we see here? The stoichiometric coefficient is 1, 1, 1, 1, same and unity. Now take this example, a second reaction. Here the stoichiometric coefficient is 2, 1 and 2. If I try to monitor the reaction by measuring the concentration or the volume of oxygen consumed during the course of the reaction, and also monitor the consumption of NO, there is a difference. During the same period, for every mole of oxygen consumed, 2 moles of nitric oxide are consumed. Therefore, if I work out the rate, I get different values. Another example, ammonia, synthesis of ammonia. For every mole of nitrogen consumed, 3 moles of hydrogen are consumed. So the rate at which hydrogen is consumed is 3 times that of nitrogen. Therefore, in general, if we want to say, stoichiometric coefficients of reactants are not necessarily unity, and they need not be equal as well. So in order to get some meaningful result, we have to find out the rate where we take into account the stoichiometric coefficients, or mention the reactant. Why that is happening? Because the rate of product formation and the rate of consumption of any reactant will differ depending on the stoichiometric coefficients. So we will go how exactly we can get over this ambiguity and get a same value for the given reaction. Take this example, H2 plus I2 giving you 2HI. If I express the rate of reaction in terms of say H2 and HI, I have taken into account the stoichiometric coefficient, so that the rate with respect to H2 as well as with respect to HI is the same. That is exactly what we have to do. Take another example. Again, ammonia. So, all reactions that all equations that we have written with respect to nitrogen, with respect to hydrogen, with respect to ammonia, we have taken into account the stoichiometric coefficients, so that the rate of reaction that we get is the same whether we monitor hydrogen or ammonia to follow the reaction. To generalize, if you take a reaction in which you have A moles of A reacting with B moles of B, giving you C moles of C and D moles of D, we can write the equation. Negative sign is used, rate of reaction with respect to reactants. If you see here, there is a decrease in concentration, that is why you have negative sign, and then here you have positive sign because the product concentration increases. So, remember that rate of reaction is calculated here is the average rate, and it is important to specify the time when we mention the rate that we have calculated. Sometimes we become interested in finding out the rate of reaction at a particular instant, say at 10 minutes or 20 minutes, we want to find out what is the rate of reaction. In such a case, we can look at the concentration profile that we have, find out at what time we want to get the rate. At this point, draw a tangent and work out the slope or the gradient, and whatever value that you get is the instantaneous rate. To get it in the form of an equation, the same expression that we wrote earlier, except that we have to reduce the time duration to 0, delta t tends to 0. That means it should be infinitesimally small, a time derivative. So, you look at what you have written. Instead of delta, we have written dr by dt, minus sign there, equal to dp by dt. Now, we also want to find out what could be the initial rate of reaction when you have just mixed the reactants. It is easy to find out that instantaneous rate at the beginning of the reaction, that is time t is equal to 0, is called the initial rate, and you draw a tangent here at time t is equal to 0, get the slope, and whatever slope that we get is the initial rate of the reaction. A rate law shows how the rate of reaction and the concentration are related. Here we have to recall an empirical observation that was made. It is very important observation. The rate of a reaction is often found to be directly proportional to the concentration of the reactants, sometimes raised to a simple power. And this observation was made experimentally by a scientist called Wilhelmy. He studied the inversion of cane sugar using a polarimeter. The concentration of sugar, that means the reaction mass, was monitored with the help of a polarimeter by measuring the angle of rotation. He observed that the rate of reaction is proportional to the concentration of sugar remaining unreacted at that instant. And because of this observation, he laid the foundation for the subject chemical kinetics, and we can call him easily the father of chemical kinetics. So, mathematical formulation of this statement is rate R is equal to minus dC by dt proportional to C, where C is the concentration. We can introduce the proportionality constant K here. so that it becomes minus dC by dt is equal to K into C. As I told you, C is the concentration. We can use this equation to find out what is K. The expression is known as rate law. Rate law is defined as the expression that relates rate of reaction with concentration, and here we are doing that. And if we put C is equal to 1, that the concentration of the reactant to be 1, then whatever rate that we get is the rate constant, and hence K is called the rate constant or the specific reaction rate. K is unique for each reaction. It has to be experimentally determined, and K changes with temperature. We know that rate of reaction depends on temperature. It's important to know that a rate law is established experimentally and cannot be predicted from the stoichiometric equation. Take this example to illustrate. H2 plus Br2 gives you 2HBr. A very simple reaction. Stoichiometry is simple. 1 mole of H2 plus 1 mole of Br2 gives you 2 moles of HBr. And we expect a very simple rate law. And look at the complex rate law that you have. You have rate with respect to bromine. You can see the power here, a fraction, and HBr, the product concentration term also appears. So rate laws can be very complicated, and therefore the relation between the rate of reaction and concentration has to be established experimentally. You cannot predict a rate law for any reaction. Looking at the stoichiometric equation, it is not possible to dictate or decide what is going to be the dependence of rate on concentration. This has to be stressed here. In other words, the rate law for any reaction has to be established experimentally. Let me summarize what we have seen today. I introduce you to the subject or the branch of physical chemistry known as chemical kinetics, an important branch where we study the rates of chemical reactions, which are industrially important. So rate of reaction, how it changes with concentration, that we have seen. There are several factors affecting reaction rates. We have discussed these factors. And finally, we arrived at rate law that relates the rate of reaction with the concentration. In the next episode, I'll discuss about order of reaction, molecularity, and integrated